Welcome to our lectures on the DC microgrid and the control. We were discussing about the design and the modeling of the DC site with the active rectifier with the voltage control voltage source current control mode of operation. Now, this class our concentration will be designing of the different kind of DC to DC converter, designing and modeling both. So, we shall talk about modeling of DC to DC converter, isolated bidirectional DC to DC converter. We shall talk in details. Nowadays, we generally prefer high power rating DC to DC converters are mostly we require a galvanic isolation and are mostly bidirectional DC to DC converter. Then we shall see also the boost DC to DC converter modeling, which can be used for trapping wind energy, and also non-isolated DC to DC converter and control of isolated bidirectional DC to DC converter, control of boost DC to DC converter. So, a DC to DC converter is a 3 terminal devices as shown in figure 1. The input terminal, the input voltage is converted into the higher or the lower voltage as required, lower voltage as switching frequency is been controlled. So, we will have a high frequency application in between, and mostly if it is isolated converter you will have a high frequency transformer. So, we can say thus a DC to DC converter is an electronic transformer similar to the step changing transformer, because you can step up and step down. What you can do in the voltage, you can do the same thing, what you can AC voltages, and you can do the same thing here. The switching signal provides the command to the switch of command to the switch of the converters that will come little later, which can be used to vary the duty cycle and thus control the output voltage. Depending on whether output voltage is lower or higher than the input value, you can have a buck converter, boost converter. You can also have a flexibility to sometime you buck it and sometime you boost it. So, thus you have a buck boost converter. This DC to DC converters are commonly used for interfacing application in DC generating renewable sources and energy storage devices. The rapid development of distribution generation and energy storage has led to the increasing popularity of the power conversion system as an everlasting key interface. So, this is something, it is gaining a popularity day by day. The DC microgrid or DC to DC converters are used for regulating the variable DC voltage in renewable energy sources like solar and wind, whose output power is varying with the input environmental condition. The bidirectional DC to DC converter provides a power link between the energy storage device and the DC bus. Isolated bidirectional DC to DC converter. This is figure shows that this is a full bridge topology, is a dual, it is called dual active bridge isolated bidirectional DC to DC converter. This is the abbreviation of it, DAB IBDC, which composes of the full bridge converter to DC capacitor and auxiliary inductor and high frequency transformer. The HF transformer provides the required galvanic isolations and that is required to protect input to the output and vice versa, and voltage matching between the two voltage level. And also if this ratio is very high, then around 10, then problem lies this control becomes very difficult with the non isolated DC to DC converter, because you may have a operation that is only very small region, and thus you may require to transfer some of the burdens in a ratio. For this reason, it has a flexibility. You can control also the duty ratio as well as you can control the trans ratio. The auxiliary inductors serve as the instantaneous energy devices. So, we can see the waveform. The figure 3 gives the traditional principle of the waveform of IBDC. So, you can see all the diagonal switches of the bridge H1 and H2 are switched by turns, and turn on angle is 180 degree. Then both the AC output voltages H1 and H2 are the square wave with, assume that, with a 50% duty cycle. In figure 2 we have seen that VH1 and VH2 are the AC output voltages of H1 and H2 respectively, and L1 is the current of the inductor L, and N is the transformer's trans ratio, THS is the half switching period, D is the phase shift ratio in half switching period, where D is within a 1, where D is a turn on by turn off. So, you can see that in this region, when current ramps on, so you can see that Q and Q3 are off and Q3, Q4 are on. Similarly, here S1, S4 are off and S2, S4 are on. Similarly, here Q2, Q3 are on and Q1, Q4 are off. This one is TSH, and in this region is T1, T2, T3, and essentially this is the current through the inductor, because you have a auxiliary inductor placed in the transformer. This is essentially the same, and this one, this red line is essentially VH1 and this green line is VH2. Just go back. So, this is IL, this voltage is VH2, this voltage is VH1, and these sites are named S1, S3, S2, S4. It is called, this is a primary side or named as bridge 1, but it is bidirectional. You can convert power this side to this side or vice versa. It is a typical case of battery charging applications. You may feed it from the grid, or you can also take it power from the grid, and you got a bridge H2, you have this reference. So, in the average transmission, the power can be derived as follows, that is P equal to TSH V1 square by L D 1 minus D by K, where K is essentially given by, it is coupled with the trans ratio, K equal to V into N into V, where N is N1 by N2. The figure 3, the zero crossing output occurs between T1 and T2 when IL T1 is 0, crossing point occurs between T0 and T1. but the expressions of the transmissions power stay the same. The unified transmission power is defined as P t equal to P by P n, where P n is the maximum power of the IBDC and is given by TSH V 1 square by 4 L. Now, let us model, we have already modeled bidirectional DC to DC converter. Now, let us come to the modeling of the non-isolated DC to DC converter, namely the boost converter, and you find many application in case of the DC microgrid kind of application, because you have a wind turbine that is generating a variable frequency DC, you require to track the MPPT, and thus you have this kind of converter to be placed. Or a PV module, you require to boost it and also you require to track the MPPT to feed the inverter voltage, there also this can be used. A PV module is a variable DC voltage source. Its output voltage increases as the sun rises, and it has maximum output at noon when maximum solar energy can be captured by the solar module. A DC to DC boost converter allows capturing a wider range of DC power by boosting the DC voltage. A boost converter consists of an inductor L, capacitor C, controller, semiconductor switch S, diode D, and load resistor R as depicted in the figure. So, this is the inductor, this is the diode, this is the switch. Depending on the switching frequency and power handling capability, it can be IGBT or MOSFET. It is a capacitor and resistance. When the switch is turned off, that energy is transferred to the capacitor. When steady state is reached, the output voltage will be higher than the input voltage, and the magnitude depend on the duty ratio of the switch. Voltage and the current relationship. The steady state analysis of this boost converter. Now, when switch is this stage is switch is closed and the stage is switch is open. Once switch is closed, that means that this switch is closed, and thus what happens, this point voltage is becoming 0 and this is higher, and thus this diode become reverse bias, and in terms when this is the duration when switch is closed. So, VL equal to Vs L didt equal to Vs by L. Similarly, when switch become open, the voltage of the source and the energy stored or the voltage across this inductor assumed to be VL. So, both will sum up and will charge the battery or the capacitor. So, the change in the inductor current will be as can be computed del I by del t equal to, you can replace del t as d of t, that is essentially is Vs by L. So, I L closed equal to, that is the ripple current present into the inductor will be Vs dt t into L. So, this is the relation between the current ripple and the different parameter associated with the boost converter. So, Vs minus V 0 equal to L di dt, and during this is the open circuit. So, you can rewrite this equation as V L di dt equal to Vs minus V 0, and thus a change in inductor current also you can compute. So, that will be the, for the open case will be Vs minus V 0 1 minus dt into t by L. So, for the steady state of operation we know that these ripples, for there will be a positive ripple and the negative ripple, are ultimately average inductor current remain same. Considering that this I L delta open and I L delta closed should be equal to 0, and we can simplify these equations and we can rewrite that V 0 equal to V s minus V d. So, assuming this converter input power is equal to the output power, the average inductor current is found by I L equal to V 0 I 0 by V s. That the dynamic modeling of DC to DC boost converter loaded with the constant power load, that is something we require to be think of. Generally, once we have a parallel circuit, within that load is connected, if voltage drop, wattage generally reduces, because it is basically proportional to V square by R. And operating the continuous conduction mode or CCM, so you can write it down L dx dt equal to E minus 1 minus U into x 2. Similarly, C d 2 x, similarly for the other parameter, for the continuous current mode, it will be 1 minus U t into x 1 minus P x. So, where x 1 and x 2 should be, x 1 is greater than 0, then x 2 should be a small number. Now, we define x 1 and x 2, where x 1 is the average inductor current, which is greater than 0, and x 2 is the, these are called the state entities, that is the voltage across the capacitor and the current through the inductor. X 2 is the average capacitor voltage V c, and U is the controllable input of the converter. Essentially, this is a switching. The equilibrium point, so x dot 1 x and x 2 dot 1 is given by definitely P v, and it is 1 minus U of t. So, this is the modeling of the DC to DC converter, and it is modeled in the, it is called average mode of modeling, and we require to compute that different mode of operation, and it is works fine, and you have this ratio holds good, considering that it is in a continuous mode of conduction. Briefly, we will have to touch upon these things, because we cannot go to the detailed modeling, you are required to refer to the DC to DC converter book. So, now let us talk about another DC to DC converter, which will be used in bidirectional operation. So, you can transmit power either direction, from battery to the load, and load itself can regenerate and send back the power. The bidirectional DC to DC converter comes from the common unidirectional DC to DC converter and can achieve energy flow in the bidirectional way. These converters, they control the energy flow direction of the bidirectional DC to DC converter, as well as the energy storage unit to maintain the stability of the DC microgrid voltage, which can satisfy the grid operation condition. Once you try to send the power, generally it will be operated into the boost mode. So, this power you require to switch it on, and ultimately energy will flow this point to this point. And so, once you try to send power this point to this point, it requires to buck it. You can see that this is a buck operation, and power can be sent back through this switch and the diode, and this has a complementary logic. The state space average model of bidirectional DC to DC converter interfacing a battery storage, typically a DC microgrid application can supply at net constant power load P n as shown in this figure here. So, you can write, that is we know that current through the inductor we have considered x 1. So, same logic has been used here, L dx 1 dt equal to V b plus U t into x 2. So, that depends on the on and off of the switch. Similarly, C dV dt, that is written as C dx 2 dt equal to U t into x 1, minus P n by x 2. So, same condition holds, where P b is the nominal battery voltage, x 1 is the average inductor current I L, and x 2 is the average capacitor voltage V c, and U is the control input to the converter. Assuming that the system on the right hand side of the converter consists of both CPLs and constant power source, the net load power P n can be positive or negative. The equilibrium point x 1 and x 2 definitely can be recalculated, and you can find out x 1 and x 2 equal to P n by V b and V b by U t, where P n is positive in discharging mode and where P n will be negative in charging mode. So, now come to the control of isolated bidirectional DC to DC converter. So, in view of the power control of the isolated bidirectional DC to DC converter, they can be classified as PWM control converter, frequency control converter, and the phase shift control converter. So, PWM control converter uses a pulse width modulation technique to adjust the converter output voltage, thus regulating the power. And second one, the output voltage of the converter is controlled by the duty cycle or by the duty cycle of the PWM signals of the power switches. And next is the frequency control converter uses operating frequency to control the power transfer. This type of converter usually contains a resonant tank which can suppress the undesirable frequency component to regulate the power gain or output gain. The duty ratio of the PWM for all the switches are fixed around 50 cycle percent, and the operating frequency changes is changing according to the conversion gain of the converter. So, resonant converter is a very good candidate for the fixed voltage gain application, since it can achieve very high frequency, very high efficiency when operated at the resonant frequency. And now, let us come to the phase shift control bidirectional DC to DC converter. It is mainly used for a different kind of dual active bridge converter. The power flow bidirectional and the magnitude can be simply controlled by adjusting the phase shift between the VH1 and the VH2, which we have seen in the figure previously. The converter in phase shift control can be represented by a simplified scheme comprises of the two square wave voltage sources linked by the inductance. Now, let us come to the next topic, that is control of boost DC to DC converter. The DC to DC converter comprises two elements, one is controller, another is the power stage. The power stage incorporates the switching element and converter the voltage to the desired output level. The controller supervises the switching operation to regulate the output voltage. The two are linked by the feedback loop that compares the actual output voltage with the desired output voltage to deprive the error voltage. The controller is key to the stability and precision of the power supply, and virtually every design uses a pulse width modulation technique for regulation. There are two main methods of generating the PWM signal. One is we shall discuss voltage control mode, another is definitely the power control mode. So, this is the voltage control mode. You have a solar PV panel, we have taken a practical application, we have to require to maintain the regulated voltage to the load. The voltage mode control is measured value and the reference voltage are compared to generate the control voltage. Then the control voltage is compared with fixed frequency sawtooth waveform to determine the duty ratio as shown in the figure 7. So, this is the PV panel, then you have a input capacitor, then you have a inductor, and thereafter you have both the switches. It can be internally power converter, or you have to increase the current rating, maybe due to that reason you require the 2 switches, then followed by the diode, and ultimately you will have the reference signal, reference voltage here, and that can be compared with the actual voltage, and this is essentially error amplifier. Error amplifier may be made to the PI controller by connecting a capacitor and with a resistance with a particular bandwidth. Then it is compared with the sawtooth wave, and the sawtooth wave is fed to the, with a limiter it will be fed to the switches to control the duty cycle of this Q1, Q2, and thus voltage will be maintained here. But one of the disadvantage, one of the advantage of this thing is that very easy to implement. Disadvantage is that it does not have a inbuilt short circuit protection. So, the voltage mode control has the drawback of the slow response to the load variation. Since this capacitor will be there, so it will change slowly, it will not act fast, and loop gain that varied with the input voltage. If the voltage of the input side is varying, then there is a also problem of this control. So, in addition to the voltage control, you can have another loop that is called the, this part is same as a voltage control, that you have a, this is called, the 2 kind of control, one is average power control, average current control mode, another is peak current control mode. This control method is more complex than the voltage mode. It consists of the dual control loop, namely the voltage and current control loop as illustrated in figure 8. This part of the control is the voltage control, and this part is the current control. In this method, the output voltage V0 and the reference current Vref is compared to generate the reference voltage Vref. The reference current Iref is then compared with the sense sawtooth waveform current from the voltage to generate the switching ratio. So, here since it will be peaky, so this current is taken and it is compared with the actual reference. The sense inductor current tracks the reference current Iref, and the output voltage V0 equals to the V reference. There is a disadvantage, only disadvantage of the control method is that subharmonic oscillations, chaos, all those things are the nonlinear phenomena occurs, which occurs when duty cycle exceeds the 50% of the duty ratio in the peak current mode control. These are also a control challenge. This different mode of control method has, this method has a following advantage, that is improved transient response, better line regulations, self protection features. It is inherently protected from the short circuit, which is absent in the voltage control mode, and compact sizing. These are the few things, and designing is simpler. So, considering that, we generally prefer self mode current control. Thank you. Thank you for your attention. We shall continue to our discussion with the DC microgrid. I hope that these discussions will be very useful to you. Thank you.